Theoretical computational neuroscience is a part of neuroscience, but with this kind of a specialty of applying mathematics and computer simulation to data.
The brain, in addition to being a biological organ, is also a computational organ because it has to do computational tasks like seeing, moving, making decisions. And so we want to understand that from a theoretical perspective.
There is absolutely no way of understanding the brain without theoretical and computational neuroscience.
When I was growing up, I was a budding scientist. I even built a working volcano. When I lit it in the classroom, it filled with smoke, the fire alarms went off, and I became known as the person who builds things that actually work.
The consistent thing that I remember is taking things apart. My father was an applied physicist and kind of an engineer, and once when I was really young, he bought a new amplifier, and rather than plug it in and listen to the music, first thing he did was take the box off, and he and I kind of peered inside it to see how it works. That curiosity is still what drives my science.
My father, he worked as a scientist. His bookshelf was completely chaotic mix of books on the Jewish law, on the Torah, a book on the integral and differential mathematics, or some encyclopedia. That was the kind of spirit at our home, and this is the legacy that he left for me.
When I was growing up, I was really good at putting together picture puzzles. My parents, when their friends came over, they would bring them over to see their son was a puzzle solver.
I was never really a hardworking student in younger days. I had a lot of fun, I had wonderful friends. You know, school with me was almost more of a social thing.
I loved poetry and I loved literature. I was mediocre in math and in physics, but at the last year of high school, something happened to me where all of a sudden I started to excel in math and physics, and I loved it.
I've always been fascinated by the heavens, the stars, the galaxies. And so I went to Princeton University for my graduate studies in relativistic astrophysics. The puzzles have gotten more complex, but ultimately I'm still a puzzle solver.
I was a professor of physics. A lot of my work had to do with space. Cosmology is kind of mind-boggling. It's such a miracle that you can write down some equations and then you measure the thing and it works, essentially perfectly.
Astrophysics was the love of my life. I had achieved my goal, which was to become a PhD in physics, but the problems that were left to be solved were so difficult that you either had to be a genius or you had to have access to data from larger and larger particle accelerators, which were costing enormous amounts of money.
Experiments got very long. You have to be extremely patient and wait many years for the experiments to come around. So I started looking around for other things to do.
When I finished my PhD in physics, I went to Harvard. I was looking for problems which are poorly understood, where I can really make an impact. I decided to focus on spin glasses. So my studies of these structures revealed the world of physics of disordered systems. And that really initiated my entry into neural networks and the mystery of the brain.
Really, the fact that I managed to get a career in neuroscience is very much due to Yves Marder. We were looking in the physics department at electronic circuits. One of my graduate students came to me and he said, "You should go to Yves' lab, it's great, it's fun." I went over there and the audio monitor was on. The circuit that Eve was studying generates a triphasic rhythm of the sound of the neurons, and I just thought that was fantastic. I walked out of that lab convinced I wanted to become a neuroscientist, which was both exciting and terrifying because I was a professor of physics. I didn't know any neuroscience. I didn't have any grant in neuroscience. So I kind of figured, well, this is going to end my career, but at least I'll go down doing something interesting.
The first stage of that career change left us more or less isolated. Physicists saw what we did as not physics but biology. And biologists were wondering what physicists have to do in neuroscience.
The brain seemed as mysterious as the universe, but you didn't need instruments that were cost billions of dollars. And I went to my first neurosciences meeting. I loved it. I felt that with my background, I might be able to actually create mathematical models of all of the complexities of a neuron that could help us explain their function. And that's how I got into neuroscience.
When we started transitioning to neuroscience, we formed a coalition of researchers from the medical school, from the life science, and mathematicians. The terminology was different, and we spent considerable effort to, first of all, establish a common language.
My work is a collaboration of experiment and theory. A theory can be beautiful, it can be clever, but it can never be true by itself. The truth is in the hands of the experimentalists. And I had an idea, and I went to Eve and I said, here's my idea, you know? And she said, well, check it out, we'll see what happens. And so, you know, I kind of went back a day later and she said, you were wrong. And I was so happy because in physics, that could have been a 10 or 20 year period. I like that immediate back and forth. Of course, I'm even happier if they say you're right, but it's okay. If they say you're wrong, you move on.
Back then, it was generally believed throughout artificial intelligence engineering that neural networks was a dead end. Jeffrey Hinton and I were listening to a lecture by John Hopfield, who was a distinguished condensed matter physicist, and realized that his network could be converted, and that turned it into the Boltzmann machine. Once we had developed the Boltzmann machine learning algorithm, we showed that, in fact, they were wrong. Neural networks wasn't a dead end.
The first research discovery was the most direct adaptation of the spin glass concept and the spin glass mathematical tools that allow us to map the properties of a neural network involved in memory, that allows us to make predictions about the macroscopic functions that emerge from the microscopic structure of the brain.
In my work with Nate Sautel on electric fish, Nate measured a number of cells that were very difficult to record, but in order to understand how the circuit works, we really needed to have large populations of those cells. So we modeled the ones that he had recorded and were able to show what that full population could do.
At the time when Jeff and I were working on the Boltzmann machine, we thought we had figured out how the brain works, but it still took 40 years, right, to get to the point where we are today. But it all grew out of this little seed that we had in the 80s.
The Brain Prize is a recognition of the field, recognition of the important role of theory and computation in understanding the brain.
Honestly, this prize is an extremely gratifying moment. For me in particular, coming into the field late, coming in as an outsider, as somebody really with a different training, this is a wonderful moment.
The Brain Prize actually throws a spotlight on you, of course, and your field, but it's more important, I think, for the younger generation, people coming up. It helps them because it gives them more prominence. That's ultimately what's important. That's really where the future is.